All right, sorry about that. A little bit of technical problems here. So let's jump into our next lecture here. Before we start, a few announcements. Office hours, you're starting globally, you are starting to use them more. Okay, there's no such thing as using too much office hour in a programming class. Okay, so I just want to remind you again, if you have problem with anything, please come and see us. The TAs just finished grading IE02. They are going to contact some of you, send a little canvas message, invite you to come to their office hours. If you receive such an invitation, I really recommend that you take it. Okay, that means that there are a few things we can help you with that are going to make the final a little bit less of a massacre for you. Okay, so take this invitation really seriously. A couple of things that they brought up to my attention, the TAs did. Some of you have been cut and pasting from the instruction, like when there is a message, we tell you display this, you just cut and paste into your Java code, right? Be careful when you do that. So there is a safe way to do that. I wrote it here. You use the edit menu, paste special, and you choose to paste as RTF. That way, if there is any special formatting, it's going to be stripped by JGrasp. Otherwise, what has happened to at least one of you, probably more, is that you did a cut and paste of a simple message, not even code, just a simple message, a string that you wanted to display, and then your program stopped compiling. Okay, so it didn't stop compiling because of a syntax error. It stopped compiling because what you did is you injected some characters that were from a different char set that what JGrasp expected. So if that happened, just undo immediately. Worst come to worst, retype the sentence or whatever. Don't spend like half an hour trying to get that to work in an exam, but I wanted to give you a heads up. The compilation issue, it's kind of like linked to that, right? If you do anything and it doesn't compile, you cannot afford to let it go. So you keep at it until it compiles. If your code doesn't compile at the end, we cannot give you points, okay? So be really careful about those kind of things. Good news, we are going to drop the worst, it's already done actually in Canvas. So we are going to drop the worst GQ grade and the worst IE grade. So that means that if you have problems, like a medical problems, like things like that, still contact me, okay? Work with me, that's completely different. Anything that we can document officially is a major problem, we handle those differently. But what's happening is that I get students contacting me for like little incident, little issues, etc. I cannot grant a retake for that because most of the time these are like issues that we cannot document. But I don't want you to fail this class because of one little problem or a bad day or something like that, or I had a migraine and I still decided to take the exam. So that will help a little bit, okay? That's the goal there. Next, I have two students so far that found some problem. One found a problem in the lecture. I think that was you. Send me a Canvas message, by the way, to remind me, okay? And another student who was exchanging Canvas message with me didn't directly find the problem in the gradebook, but his question led me to actually realize that you guys were not getting full credit for the first GE. So I'm decided that when this happens, I'm going to try to do something like extra point at the end of the semester or something like that. So I haven't decided exactly what I was going to do. But if you find a problem in the slides, a problem in the gradebook or something like that, post in Canvas, okay? And I will try to get you some bounty before the end of the semester, okay? All right, now let's jump back into the flow. So we are still on module 4. Depending on how things go, we might be able to wrap up module 4 today, or most likely we're going to focus on data casting here, this session. Maybe start a little bit of the number system or finish it next session. So somebody asked, I don't remember if it was a Canvas message or on Piazza, but somebody asked, is this all going to be on the next IE? Is the IE at the end of the week? Yes, up to data casting, okay? So the data casting part is going to be as a menu for the next IE. The number system, no, it's going to be on the GQ, PQs and stuff like that, but not the IE. So what is data type casting? So we've encountered it already. And by the way, this morning I saw a very good question on Piazza again about, elevating to the power 4 and elevating to the power 1.5. Okay, so if you haven't checked it out, check out that question in Piazza. It's worth your time. There's a lot of stuff going on here in that question, in that example, which was from one of the PQ, that goes a long way to make you understand how different things are in computing compared to mathematics. Okay, that thing I keep telling you, it's not just about the value, it's about their data type too. This is the best illustration I could have come up with. Somebody else brought it up in Piazza. Okay, so what we are going to deal with here, we're going to deal with all those kind of things that we have encountered, and I'm going to try to kind of formalize them. So now we're going to cover them officially pretty much. And then I'm going to add another layer. So there are going to be two types of conversion, the ones that we kind of dealt with until now, but we didn't talk about them a lot, and the ones that we are going to learn to craft by hand right now by taking control. So it's all about those kind of expressions, right? Byte I equal 100. Nothing is innocent in programming, okay? So when you look at byte I equal 100, it's not 100. It's the integer literal 100 or the integer literal 100 of data type int. Yeah, that's how you need to think when you program, okay? Even if you use Python or a language with dynamic typing, okay, that doesn't insist on you putting the name of the data type every time you need a variable, you still need to think like that. So I'm assigning an int to a byte. That can be a problem because I know the byte is a tiny integer type, so int is slightly bigger, okay? So here we have a bunch of binary operations, so operators with two operands. And if you look, we have, in the next things here, we have a bunch of different data type with one another. Like this is a byte, this is a double, this is a long, this is an int. So the last one is actually the best of the lot. I mean, it kind of put like 4 data types together in one equation, and we expect the result to be a double. So that sort of deduction that you have to go through when you try to figure out, okay, so what is the data type of my result? This is data type inference. This is data type deduction. Java does it. Now, our job is to know how Java does it, so that when we write something that Java needs to execute, we know how it's going to interpret it. So the rules are pretty simple. When you have an operator, if one of the operand is a double, the other is converted to double. No question. So if I try to add an int to a double, and I already mentioned that rule, right? So now we put it down on the slide, it's official, right? So if I add an int to a double, the int gets upgraded to double. Why? Because the int is a small data type, the double is a larger data type. You always go from the small to the larger data type. What if one of the operand is a float? Well, if one of the operand is a float and we didn't trigger that rule, that means that the other operand is anything but a double. Guess what? Anything but a double gets upgraded to a float. So if we have one operand that is a floating point number, we switch to floating point numbers. That's the first rule, okay? Now, if it's a double, we switch to double. If it's a float, we switch to float. And then, what is the next biggest data type that we have? That's long. The next biggest numerical data type that we have, I should say. So the long is the largest of the integer data type. So if one of the two operand is not double, none of them is double, none of them is float, one of them is long, then we are going to convert the other one to long. So we have this order that we go through, that checklist. And then at the end, if both operands are not meeting any of those 3 rules, that's it. We just convert both to int. And these are the rules that are followed by Java. So they kind of make sense, okay? We already started talking about go from smaller data type to bigger. We started talking about, if you have a floating point number, just go to floating point for the whole thing. So it's still there, but now you have the full details, including the last step, which is, hey, you know what? If none of those rules apply, then it's going to be int conversion for both operands. So now you have the whole story. So these kind of conversions from the previous slide, these are the ones that happen without us having to do anything. That's neat because we don't have to worry about it, but that's also a trap because that means we can go like, I don't know, this is week 5 now or something like that. We can go 5 weeks into an introduction to programming without actually knowing exactly what the code we write is doing. Okay, we kind of have a vague idea, we guesstimate, etc., educated guess, and we kind of make it work like that. Now you know exactly how the conversions are going. Well, there are other conversions that are not done automatically for you, where you have to actually write the code to force Java to do the conversion. These are called explicit conversion, okay? So here's the kind of like the whole picture. The implicit, so we're going to have a lot of synonymous, right? The implicit casting or data type casting or data type conversion, all of these expressions are used to mean the same thing, right? So the implicit casting that we were talking about, here's an example, double D equals 3. It's also referred to as type widening because you go from a smaller data type to a larger data type, or also upcasting. Okay, so I gave you enough vocabulary to be sick and tired for the rest of the lecture. Sorry about that. But yes, these are all of the different ways people are going to refer to that concept. The concept is simple. So I have an int, it's a small data type. I'm going to shove it into a double. Yes, I can do that. Implicit. That's what we had on the previous slide, okay? Now, the second type of typecasting is a explicit typecasting. So take everything, every jargon, piece of jargon that I gave you and kind of flip it around, right? This is implicit, this is explicit. This is type widening, also known as type widening, type narrowing, okay? This is called upcasting sometimes, this is called downcasting. So the idea is we are trying to cast values, but we are not going in the natural direction. The natural direction is I have something small, I want to put it in a larger bucket, sure, why not? Now we have something big, we want to fit it in a smaller bucket. We are going to lose something. That's why it's not done automatically by Java. Java doesn't even want to take a chance. It looks at your data. It doesn't know the value of the data, but it looks at the data and says, wow, this is 64 bits of data, and you want to show it into a 32-bit variable. I'm not touching that with a 10-foot pole. That's what the compiler tells you whenever it pops that computation error that say possibly lossy type conversion or possible loss of data. Okay, that means exactly that. That means I looked at the size of the string, that's not going to work, right? But sometimes it works. Like if I want to store 0, how do I represent 0 with 64 bit? 0, 0, 0, 0, 0, 0, 64 zeros. What if I want to assign that to a 32-bit variable? I can represent 0 with 32 zeros, right? So yes, in theory, that data type is larger than that data type, but the actual value will fit. That's why we need explicit casting, because the compiler will never try. If it just looks at the size of the data type and say, no, it's not going to fit. But sometimes we know better. As programmers, we know that the value will fit in a smaller bucket. We have to have a way to force the Java compiler to let it go, to accept that we are going to do one of those quote unquote dangerous, potentially dangerous type conversion. So what is a syntax? Well, here's an example of declaring some variables, okay, and initializing them, kind of like following that example here. But this time we are going to try to assign a value that is of a larger data type than the data type of the variable. So our variable is going to be int I in both examples, okay? I'm trying to assign 3.0. If I just write int I equal 3.0 semicolon, compilation error, no problem. So now I want to force the compiler to accept that conversion. I use the syntax. I put a pair of parentheses, and I put that pair of parentheses right before the value that I want to convert. So in the middle of the parentheses, I just have to specify the data type that I want to use for the conversion. So parentheses int followed by a value or a variable or an expression, that means take that value and convert it to the data type int. So I take 3.0, which is data type double, convert it to an int, assign the result to the variable I, which is of data type int. We're good. So what happens when I do this? So what happens when I do this particular assignment here? Well, nothing. Everything goes well. There's no problem. Why? Because 3.0 as a floating point, I can, with 100% accuracy, represent it as an int. It's just going to be 3. So here and here, these are two different types of data type conversion. But what they have in common is that we don't lose any data. Now, let me bring your attention to that one here. the one at the bottom. So the one at the bottom is still the same template, right? A double value. I'm going to convert it to int. So double is a large data type, int is a smaller data type, smaller range, smaller number of bits. And then I'm going to assign the result to an I that is itself an int. So it's going to work again. The compiler will let it go. So the whole purpose of that syntax is to tell the compiler, I know better. I, the programmer, know what I'm doing. Shut up, do that conversion. But in that case, there's no loss of data. In that case, guess what I'm going to lose? The 0.9. Okay, 3.9, convert that to an int. There is no way to do anything but lose the 0.9. Okay, you go from floating point to integer. Guess what? You keep the integer part of the floating point number, and that's it. That's the best you can do. So I have lost some data. Sometimes I'm okay with that. Okay, by default, Java doesn't accept it because it's risky if you don't know what you're doing. I have the syntax to tell Java pretty much, shut up, let me do my job. I know exactly what I'm doing. Okay? So we use explicit casting when there is potential data loss. Another way to look at it is here's a list of numerical data types. I ordered them from the smallest to the largest. So smallest means the number of bits they occupy in memory, but also the range of value that they can accommodate, right? And whenever you are trying to go this way, you are actually trying to do an implicit casting. Whenever you're trying to go that way, then this is where you are going to have to do an explicit casting to avoid the compilation error. So an example of, what do I mean when I say, shut up, I know what I'm doing to the compiler? Well, take a look at this piece of code. What is it doing?
It's converting the double tax to an int.
So at some point here, I have tax. Tax is, where is it declared? There you go. Double tax is purchase amount times 0.03, okay? Purchase amount is declared here. It's whatever the user types. We ask the user to type to enter the amount of a purchase. So I bought something for $23. So my $23 goes here. Then I multiply by 6% tax. And then I say the sales tax is, and I want to display something. So yes, part of it is I'm going to convert tax, which is a double, to int. But why do I do that? I'm going to lose data. Like if it's not $23, but it's like $23.95 times 0.06, right? That's not going to be a round number. So what am I doing here exactly in the yellow part? You are allowed to tell me that what is in the yellow part looks completely stupid. That's part of the game, right? Yeah.
Oh, you're asking what's in the yellow?
Yeah, what's happening? Why are we doing this in the yellow part?
Cents and then divide it by a double just to get it back to normal form, I guess.
So I wouldn't say normal form, but I think you got the idea there. We are, okay, look at it from a mathematical point of view. I take tax, I multiply it by 100. I convert it to an int. Well, so that's not really mathematical, but okay. And then I divide tax by 100. If I multiply something by 100 and I divide it by 100, I didn't accomplish anything, right, in math. Well, with data types, it's different. So let's say that my tax amount here, the tax amount is $3.96, whatever. So I have $3.96 is a bad example. I have $3.9675 for 4 digits after the decimal. So I have my $3.9675 here. I multiply by 100. So I multiply an int, 100, by a double, I get a double. So I forgot the number, 395, 96, 70. Thank you, 396.75, okay, multiplied by 100, that gives me 396.75, okay? All right, and it's going to be a double because int times double gives us a double. Now I convert that to an int. Explicitly, I lose the 75 that I could not remember anyway. So now I'm left with 396 as an int. So I truncated by converting to an int. I truncated the decimal part, and then I take this 396 as an int, and I divide it by 100.0. 100.0, it's a double. Divide anything by a double, you get a double. So 396 as an int divided by 100.0, that gives me 3.96. So what I did here is I just played with moving the decimal dot, right? I moved it 2 places to the right, truncated, like switching to an int, everything that was left after the decimal dot, then moved back my decimal dot 2 places to the left, and there you go. Okay? So it's a trivial example. What I mean is that like the utility of that thing, we can do that differently. We don't have to do it like that. That's why I say it's trivial. But it still shows that sometimes, yes, sometimes we want those conversion, even though they lose data. We want to truncate. When we want to truncate, we can do it like this. All right. So that part here, again, moves the 2 digits. This one drops the fractional part, pretty much. The conversion is doing that for us. And then get it back to the ball. And then we have a program that displays the cell stacks with 2 digits after the decimal point. Going back to module 1 to 3, remember that part where I said you have to read the requirement and you extract a small part of the requirements, a small goal, and then you try to figure out how you're going to implement that goal by looking in your memory through all the building blocks, all the code examples that you've seen, and you try to find something that looks very similar so that you have an idea of how to start implementing that goal. If I write this, I know because I've done it in the past, if I write this, there's going to be a portion of students, the number of students vary every semester, of course, but there's going to be a portion of students that are going to have trouble connecting this, display the cell stacks with 2 digits after the decimal point, to that type conversion with loss of data to an int. Yes, that's where it starts getting a little bit more complicated, okay? Module 1 to 3, I always try to give you, and I know it was not obvious for everyone, but I try to give you always a goal that could be mapped directly to a building block. And the mapping was relatively straightforward, just so that you develop that skill, okay? Of course, at the beginning, it was not straightforward. But now I'm telling you, I'm warning you for the next step, okay? The expectation in programming are that sometimes you're going to have people look at you and tell you exactly what they want as a result. And the way they describe the result can be sometimes a little far from the how to do it, right? So how do you reconciliate this? There's no magic. You have to go through a lot of code example. You have to try to code stuff. You have to fail, remember your mistake, understand your mistake, move on, and stuff like that. Because what you are dealing with here is you need to build experience. Once you have been exposed to that, maybe somebody is not going to ask you to display the tax cells with 2 digits only, but they are going to phrase something different in English, but it's going to boil down to, I want to keep only 5 significant digits in my result. Well, that's another way to say exactly the same thing, right? So when you see that kind of requirement, you're going to remember that example. You're going to say, okay, I kind of have an idea that, using truncation with data type conversion is going to help me. And that's all you need. You need a beginning point. And then you experiment, you try, you see what works, what doesn't work, and you refine your solution. Another thing that I need to mention, we talked about those assignment operators last time. We talked about the augmented assignment operators, right? X plus equal 3, Y divided equal 5, and stuff like that. Okay, so the format is a variable name, an operator followed by the equal sign, and then here an expression. Okay, I put a variable there, another variable name for simplicity, but it could be a whole expression. And I told you that this was just actually translated by the compiler into a full expression, and then this is what was compiled into your code that run. One thing I omitted here is this data type conversion. To make this work, what actually Java is doing is taking your n plus equal 5, for example, and it's doing n equals n plus 5 converted to the data type t, knowing that the data type t is the same data type than x1. So it looks up the data type of the variable. It say, okay, you want to assign to an int? All right. So this is going to be that variable is assigned. Just to be safe, convert the result to an int, make it explicit, and then do your formula. So that means that when you use augmented operators, and again, this is to point your attention, to draw your attention to what is dangerous, okay? You can explain the augmented operators very easily. Like last time I did, n plus equal 3, that means n equal n plus 3. Well, I mean, you may find it weird, you may not like it, but if your life depends on remembering that fact, everybody in this room can do that, right? But then you scratch a little bit under the surface, you start learning about data type conversion. And now what I'm telling you is that if you write things like this, there is automatically an explicit data type conversion that's going to be done. Which means what? You lost your agency. You lost the capability to decide whether you wanted actually an explicit data conversion and add that syntax, parentheses, int, etc., or whether you wanted Java to warn you if there was a type conversion going on by telling you, hey, this is not an implicit one. I'm not going to try to do it. You should watch out, okay? So that, I've never seen it cause a real bug in COP2512 or 2513. So that's the good news, right? Like whether you understood what I just explained or you didn't quite understand it, you should be still safe. But I just want to give you a taste of why details matter, why understanding, what is going on under the hood actually makes a difference. Because as you write more and more complex pieces of code, the chance is that one day this is going to actually make a difference, and you are going to scratch your head saying like, well, I don't understand. I did the x plus equal, and this expression, and the compiler didn't tell me that I was going to lose data, so the expression is right. So then you move on and you look for your bug elsewhere. No, the bug was probably right there. You got a roundup that you didn't expect or something like that. So here's just a code example that's going to kind of reiterate this and on something concrete. Int sum equals 0, so sum is of data type int. Sum plus equal 4.5. And then the question is, what is the result assigned into sum? Okay, so we know 4.5 is a double. We know sum is an int. So red flag, right? There's going to be some explicit conversion here. Do I have the syntax for an explicit type conversion? No, I don't. I didn't put any parentheses int here before the 4.5. However, because of that, I know that this line is going to be rewritten by Java like so. So there is a type conversion here, right? So it's going to do sum plus 4.5, which is going to give me a result that is a double, by the way. So sum is 0. 0 plus 4.5, 0 is going to be translated to 0.0. The result of 0.0 plus 4.5 is 4.5. And then 4.5 is converted forcefully into an int. So I cut off the 0.5, I get 4, and then I assign that to sum. Okay. Again, check out on Piazza. Like the question that was asked was a great example of how sneaky that kind of stuff can get. Okay. So don't get mad because it's sneaky. All right. Get happy because now you know better. Okay. That's the difference of attitude. You are not getting hindered here because, Java is really trying to get me at every corner. No, that's not what's happening. Even if it feels like that at the beginning, what's happening is that now you are getting knowledge that allows you to masterfully use the Java language, okay? And you'll remember that term masterfully, like next time you have to deal with a bug, you're going to be like, he was joking or he was sarcastic. No, that's how we develop mastery, right? All right, practice exercise. Here's a practice exercise to help you let that sink in. So print a table. Do not use a loop to do it, okay? That's an added constraint that I put on top. This chapter doesn't cover loops anyway, so they don't expect you to use a loop, but you guys know how to use loops, so you might be tempted to do so. Now, do not use a loop, do it by hand. That's the practice right there. And we have time for number systems. So that means that we are going to probably wrap things up this session. All right. So number system is a totally different topic than data typecasting. It's not going to be as a IE coming up this week, okay? But it is at the PQ and GQ. Like I said last time, this is actually something that people generally learn in computer organization, if they take that class, or discrete math. Okay, discrete math is another class where generally we cover number systems. So I'm just going to do the first part of it, the minimum. Okay, what do you need to know about number systems right now so that the rest of the class doesn't get progressively more confusing? So we're going to get out of the way a small introduction to number systems. So the basic idea is when you look at 423, well, the first thing you should know is that we use base 10 by default, okay? I don't know many human beings that you walk to them in the street, you ask them for a solution to a math problem, and they give you the solution in anything but base 10. That's what decimal is, base 10. 10 means we have 10 digits. And in the following of this lecture, what I will call a digit is a single number here. 4 is a digit, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to call those digits. This is a number. A number is a series of digits, okay? I'm clarifying that because a few semesters ago, I didn't realize that I had a confusion and some of my students thought that digits and number meant the same thing. No, at least in the following, it's not going to mean the same thing. So when you have like 423 expressed in base 10, that means that you write the number with digits that only go between 0 and 9. How many digits is that? 10. Lucky for us, we have 10 fingers, so I wouldn't doubt, that base 10 comes by the number of fingers, okay? So what that number mean, what that value mean, this is just a way to write it, right? 423. But what it means mathematically is 423. So I could take, and this is kind of an exercise in futility, right? But bear with me, we are going to apply that to something more interesting. If I wanted to translate this into its value, so I look at this like a writing, right? 423 is written on the wall. I want to translate it into a numerical value. I would take 4 times 100 plus 2 times 10 plus 3 times 1. Each digit has a specific factor associated to it, right? So those factors are the base 10, decimal base. Base to the power 0 is what I multiply the rightmost digit by. Base to the power 1, so 10 to the power 1, going to be 10. This is what I multiply the next digit by. 10 to the power 2 is what I multiply the next digit by. If I had a longer number, 1, 2, 3, 4, 5, 6, I would keep going. The 6 would be multiplied by 10 to the power 0, the 5 by 10 power 1, the 4 by 10 power 2, the 3 by 10 power 3, the 2 by 10 power 4, and so on and so forth. Okay? So I would just increase the power of my base. And that's what it means to write a number in base 10. Okay? I write 423, and this is how we all understand what 423 means. All right, so we can express a number as a polynomial. The coefficients are the digits, and the 10 power, something like that, it's always going to be the base to the power 0, then 1, then 2, then 3, then 4, going right to left. Okay. So that's the basic idea. And then, what if we change the 10? I mean, now that we have, kind of over-formalized something that is like everyday knowledge, common sense, everybody knows 423 is 423. So we kind of like wrote it as a polynomial, but what's the point? Well, the point is that now we can actually start thinking about using different bases than 10. So we can increase or reduce the number of digits that are available for us to write numbers. And that's what bases are. So when you see 423 written, from now on, the same way that when you see 100, now you're getting paranoid, you're saying this is not 100. This is 100 as an int in Java, right? Well, now when you see a number like 423, you're going to have to think about, well, wait a minute. It's not necessarily 423, because if it's 423, that means it's expressed in base 10. But if somebody is using a weird base, like a base, I don't know, 6, so 4 is going to be multiplied by 6 to the power 2, 2 is going to be multiplied by 6 to the power 1, 3 is going to be multiplied by 6 to the power 0. That's going to give me a different value, right? So that's what we're talking about. So nobody uses base 6, at least that I know of. Maybe they use it just for an exam to test the student or something like that, but really it's not a thing. But these are things. The decimal, of course, is a thing. Well, we have been using it for quite a while and we are all happy with it, so we're going to keep using it. Binary is a thing, because in actual memory, okay, or on a hard drive, what you write are always 0 or 1s, okay? There are 2 voltages, high voltage, low voltage. The whole concept of electronics, modern electronics, is based on binary. So even though I'm using 423 in my program, when I assign 423 to a variable, an int variable, for example, it's going to be translated from 423 to a bunch of 0, 0, 0, 1, 0, 1, 1, 0, 1, etc. Okay? So yes, the binary code, the binary base, we use that a lot as well. Octal, not so much. So we're going to just sweep it under the rug because this is not a course about number theory or stuff like that. Decimal, we already know it. The only other one I want to draw your attention to is hexadecimal, base 16. Why is it so popular? So the first thing that's weird with base 16 is that when you go from decimal to binary, you go from a system that has 10 digits, 0 to 9, to a system that has only 2 digits, 0 and 1. So you're like, sure, whatever. So that means I write my number with 0, 1, 0, 1, 1, 1, 1, 0, etc. What if I go to a system that has 10 digits to a system that has 16 digits? So I'm going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the digits, 0 to 9, I can write them the same way that I write them in decimal, but then I'm running out of symbols. I need more. I need a symbol that represents the 10 hexadecimal, a symbol that represents the 11-digit hexadecimal, the 12 digits, so I use letters. So in hexadecimal, your digits go 0 up to 9, and then it's A, B, C, D, E, F. And these are just digits. Each of them is a digit. So that means that in decimal, when you say 12, the value 12, I write it with the digit 1, the digit 2. In hexadecimal, if you give me the value 12, I'm going to look up my chart and I'm going to say, hey, I have a symbol for 12. The symbol for 12 is C, and I'm going to write 12 as a C, okay? So that's pretty much the only inconvenience there. We have to add more symbols to represent pretty much these digits. So you can have a number like, for example, 2A. 2A, the fact that there is a letter between A and F in the number value, that's a good sign that you're talking about hexadecimal. But you don't have to have a letter. For example, 22 could be an hexadecimal number. I don't know. So it's not sufficient to look for letters to be able to spot that something is written in hexadecimal. But this is an example of a perfectly valid number expressed in hexadecimal notation. So what about that 52 that's supposed to be in octal, that 42 that's supposed to be in decimal? And if I would have taken another example here, like 22, what about the 22 that's supposed to be in hexadecimal? If I just look at the value, I cannot tell that you are using a different base. So I need a way in programming language, but also, in everyday, well, not everyday life, you don't really do that in everyday life, but outside of programming language, let's say, I need a way to write a number and say this number is actually written in base 10. This one is written in binary. Well, that's kind of obvious. That one is octal. That one is decimal. This one is hexadecimal, because it's not always obvious just by looking at the number. So let's talk about syntax. This is how Java does it. A lot of modern programming languages have similar notation. I cannot guarantee that it's going to be exactly the same, but this has become a pretty standard way of writing literal value, numerical literal values in programming language by specifying a different base. So let's start with the nice one. This is an integer literal. What is the data type? Int. There's nothing special about it. We are going to assume that it's written using base 10. So now you can tell me this is a decimal integer literal. When you try to explain things to people, don't be over pedantic, okay? But when you try to explain things to people for the first time, or when you try to make sure that you understand things right, being pedantic helps. So training your mind to look at this and rehearsing, this is the integer literal 101 written in decimal form and of data type int. Do this for one semester, and I promise you, you are going to be a better programmer for it, okay? What about this? Do I need to put a 0 in front of a number? No. 0.5 is the same thing than 5, okay? 0.3 is the same thing than 3. So when you see a 0 starting an integer literal, there's something fishy about it. The something fishy is that we decided that if we start an integer literal by 0, that means it's in octal base. So it's easy to remember, right? 0 like octal. Well, kind of. But anyway, that's how you are going to say, I write the value 100. It's an integer value, but this is in octal. So when you want to actually compute the value of that 100 octal, you are going to say 0 times 8 to the power 1, 0 times 8 to the power 2, 0 times 8 to the power 0 first, then 0 times 8 to the power 1, then 1 times 8 to the power 2. This here is 64. Written, the value 64, written using an octal notation. And we write it in Java by using the 0 at the beginning. That means this is going to be octal notation, integer literal. I don't know why I clicked. I mean, it comes with age, I guess. But whatever. So the next one, I was trying to go in a rush there. The next one is 0x face, F-A-C-E. These are part of the letter that I can use in an hexadecimal number. I can use everything from 0 to 9 and then A to F, okay? So these are hexadecimal digits, actually. So this is still an integer literal. It is written using a notation that is hexadecimal. I can tell because of the digit, but even if what I had here was 1, 2, 3, 4, these are also hexadecimal digits after all. I can tell it's supposed to be hexadecimal because it starts with 0x. And 0x is almost a universal convention for hexadecimal notation across all programming language, okay? I cannot think of one that is using something different. And then what if I want binary? Well, if I didn't have a special way to write this, 1111, that could be, that's not octal because it doesn't start by a 0, but that could be decimal, that could be even hexadecimal. 1 is an hexadecimal digit too. So if I want to specify that this is a binary number, 0b. So 0, 0x, 0b, that's it. Easy to remember, x for hexadecimal, 0 for octal, and 0b for binary, okay? All right, and if I display those things, so the data type I already insisted every time I mentioned those values, I said they are all int. We're not talking about changing the data type. We're just changing the way that we write down the number. And when we display them, the first one is 101. Well, that makes sense. The second one is 64. I didn't mess that up. I'm proud. The next one, I have no idea, 64,206. And then the last one, 15. So the notation is one level, the data type is another level, the actual value is another level. There are three things going on when you write down a number in Java, a literal. Three things going on, and you need to be aware of that. All right. So now, what we did here, yeah, question? Yeah, sure. There we go. So when you see the 0x here, The only thing that happens, right, is that before to do your assignment, it's going to say, let me convert that to a value, right? So it's going to go through that, that polynomial that we described. It's going to say, what is the value of the first digit, E? So 0 to 9, then A is 10, B is 11, C is 12, D is 13, E is 14. So that digit, just the E, represents the value 14. I'm going to multiply this by the base, 16 power 0. 16 power 0 is 1. So this gives me 14 into the value. And then I'm going to add to that the next digit. So we are going to go through that digit by digit conversion of the notation, right? So it's kind of like we go back to decimal in a manner of speaking. And then once we have the value, we are going to say, what is the data type of that value? Int. What is the data type of the variable int as well? So I don't have to do any conversion. I don't have to mess around with data type conversion. I assign the value to the variable, but the value will be 64,206. So later, when I display println C, I'm going to display 64,206 because that's actually what is stored inside the variable. To be honest, I did kind of like half a lie here. I told you we go back to decimal and we store the decimal value in the variable. To be 100% honest, no, Java goes back to binary and stores the binary in the variable. Did that address your question?
A little bit. Just trying to figure out how you got from 14 to 6,000 or 64,026.
So I was lazy. That's how I did it. Okay, I did only the first digit. But that's why. It's like, you know, when in a book they say this exercise is left for the reader, it's because they are lazy, just like Fermat and his theorem, right? So let's go back here. How do I go from this to 64,000? The first one is 14. 14 times 16 to the power 0 gives me 14. The second one, not 0 to 9 are 0 to 9. Then A is 10, B is 11, C is 12. So now I take 12, I multiply 12 by 16 to the power 1, and I add that to 14. You see it? And then I keep going like this. This is going to be 10 multiplied by 16 to the power 2. This is going to be 15 multiplied by 16 to the power 3. And when you add up all of this, that's what you get. Yeah?
One, for the hexadecimal, is it even case sensitive like the first binary example was?
That's a good question. No, it doesn't need to be case sensitive. Very good question. That's pretty much one of the few things we are going to encounter in programming, or even if you use command line anywhere, that's not going to be case sensitive. So you can use lowercase a, uppercase a. The convention generally is to use all uppercase. So I should probably rewrite this, F-A-C-E, all uppercase. But that's a very good question. Yeah, it doesn't make a difference. No, I'm sorry, you had a good question. You cannot ask another question, but these are the rules now. Go ahead.
So wondering if there's a way to reverse it. Like, can you put in 64,206 to get AC, or would I have to like program that?
So we're going to check that out in the next slide, okay? Because like right now we're dealing with the easy stuff, which is displaying values, right? So you can write value using all those notations, and then println, kind of displays then what is the true value. Yeah.
Use variables in place of literals, or does it have to be literal?
So the notation, that's a good one too. The notation that we're learning, here's your x, you cannot put it in front of a variable. It's not like a notation that's going to convert something, right? Inside variable, we store values. So for us to keep our sanity, when I think of a variable, I think it stores the decimal value. But really, I'm fooling myself. Every variable in Java, or like most programming language, is going to store the value in binary, right? So internally, it's all zeros and one. And then here, what you do is you change the literal notation. So when I have a variable like int, for example, let's say that I assign this to C. If I do int d equals C, right? I'm not even talking about a notation here. Notations are only for literal. So I have a variable C. The variable C contains a value. Is it coded in binary, decimal, hexadecimal? It's coded in binary in memory. But when I assign it to D and then I display D, println has this nice habit to display stuff in decimal. So that makes it more readable for us. Does that make sense? There are a bunch of levels okay? I'm not claiming this is trivial, okay? Eventually, you'll get to the point where you look at this, you say, oh, okay, that's the old stuff I learned, 20 years ago. It's trivial now. But the first time, part of the learning experience is the first time you look at this, there should be a certain degree of shock, okay? Where you're like, are we talking about just numbers here? Yes, we are. But this is the second part of the course, right? First part of the course, I was glad to tell you assign 5 to x. That's it. Assign 5 to x, display x, you get 5. Wow, I know how to program, right? Well, yeah, that's the first step. But now we need to go a little deeper. So all of those problems are things that you need to be aware of. So the first time it's weird. Yes, everything new is weird, but we are going to get you used to those things, okay? Because I'm going to keep repeating them until you're sick and tired of them, pretty much, okay? So, but that works. Now, the second question was, how do we, go the other way around? Okay, so it's going to be a little bit more syntax. So I'm going to give you the syntax. We're not going to use that a lot. Again, I'm not going to insist on the number system. I just want to demystify number systems, and then you'll have other opportunities to drill through them and learn to use them if you need to learn to use them for your daily work. So I want to do a system.out.println, but I have this value here. That's actually 777. And what I know is that whoever wrote 777 didn't mean 777. They meant 777 as an integer literal written using the octal base notation, base 8. So how do I decrypt 777? Okay, so we go back to your question over there about like the 64,000, right? I take 7 times 8 to the power 0, so that gives me 7. I add 7 times 8 to the power 1. I add 7 times 8 to the power 2, and I add all of this together. That gives me the value in decimal, okay? So here, what I'm doing is I'm taking that notation, 777. I put it in a string. That's the first step. I put it in a string. And then I call that method integer.parseInt. So that method is supposed to take a string, find an integer value in that string, and convert it into a value. But the side effect of that method is that you can ask that method to read a value, a literal, right, as decimal. That's what it does by default. Or you can specify a second parameter, which is going to be the base. And when I specify parseInt, double quote 777,8, I mean, read that string. There's an integer in it, an integer literal. Decode that integer literal using base 8 octal. So it's a little different, right? When we write literal value in our programs, we use that 0x, 0b, 0, prefix in front of the literal. When we have values like variable, etc., and we want to decode them, etc., it has to go through a string. Because a string is what gives you that step of, this is a notation. It's not 777, it's 777. And now we decode this base 8. That gives us a result here. All of this is substituted by the result of the conversion. And then what I say here is integer.toString, so convert a value, a numerical value that's an integer value, convert it back to a string. And I'm giving you the value that I computed here, and I say convert it back base 10. And that gives me a string, and the string is finally displayed by println. So yeah, there's a little bit of workarounds here to do to get that, okay? But if anything, that example is just underlying again the difference between the notation of something, the value of something, and the data type of something. These are like 3 different things. All right. Another thing that this example, that's why I kept it. I was this close to skip it because really this is not too important for this class. But the reason I kept it is because it illustrates method chaining. And method chaining is something that I want you to get progressively comfortable with. It's one of those things that if you see it in somebody else's code, I want you to understand it. Do I ask you to chain your method when you write your own code during the final exam? No. Write the code however you know how to write it, however you are familiar with. But look at what's going on here. I call system.add.println. This is the opening closing parentheses for system.add.println, right? The whole thing. What I pass to system.add.println is the result, the return value from calling integer.toString with this parameter. Okay? So to be able to call println, I need to first call integer.toString. To call integer.toString, I need to figure out what is this parameter, what is this one. This is 10, that's easy. What is this one? To figure it out, I need to call integer.parseInt. And whatever result is going to give me is going to be the first parameter for integer.toString. The second parameter will be a 10, then whatever value is returned will be the only parameter for println. So you can nest like that, calling your method. I already kind of blurted that out. Remember when I told you an expression, wherever you have a value, for example, whenever you expect an int value, you can substitute to a literal or a variable of type int. You can substitute any expression you want that's going to yield an int value. While calling a method, if it's a method that returns a value, that's also an expression. So we could have formulas here, we could have like very complex stuff, but it boils down to what is the value of this thing? What do I do with the value? What is the value of this call here? Then when I have the value, what do I do with this value? I put it with 10 and I send it to string. What do I do with the result? I send it to println. And it's just a slightly more complicated version of that. System.out.println math.square root of 36. If you understand this, I have 36.0. I pass it to math.square root. Math.square root returns to me 6.0. I pass 6.0 to println. Println displays 6.0. If you understand that example, you will understand that example. All you have to do is get over the fact that, yes, this one is a little more complicated. Break it down. It's made of the building blocks, the same kind of constructing blocks than the example at the bottom. So we talked only about integer literals until now. Okay? Can we mess around with floating point literals? Of course we can. What would be the fun in not being able to mess around with those? Is that going to be the same thing? Of course not. If it was the same thing, it would make sense, right? So we're going to have some exception here. We're going to have, again, a few things to watch out for that are going to help you differentiate, a good programmer from a bad programmer. All right, let's take a look at the code here. Double A, so variable A of type double, we're okay. So far, we are good. Equal 100.1.230. So by now, there should be at least a few of you that are looking at this number really weird. Even though it's perfectly normal, it's just a double, just a double literal, right? Maybe I successfully gave you enough paranoia that when you look at a literal, now you ask yourself, hold on, what base, what data type, etc. If anything, the 0 at the end should throw you off a little bit, but there's nothing that forbids me to put a 0 at the end. Does it have a special meaning? No. So that is not meaning octal or something like that. Octal is only if you put the 0 at the beginning. So I'm going to try that. Double B equal 0.123.222. Hey, this is what we do with integer literals. So I'm going to do it with a floating point literal. That should work. It should. It doesn't. Java doesn't actually allow for octal floating point literals. Why, you ask? It's a good question, answer. I don't know the answer. Okay, I don't know why they didn't go with octal base for floating point literal. Maybe nobody was using it, nobody cared, something like that. I don't know. So that one is wrong. We cannot just prefix with a 0 and expect these digits to be interpreted with the octal notation. This is just 123.222. That's it. So, all right, first try, we got it wrong. Second try, we are going to get it wrong too. What if I use what I learned about hexadecimal integer literals, and I try to write a floating point hexadecimal literal? So 0x and then 123.222. That should work. It makes sense. That is not a valid Java syntax. So those two things, they are arbitrary. I'm just warning you. I'm not trying to make you buy that this is a good idea or a bad idea. I'm not trying to defend it or, condemn it. I'm just telling you this is what everybody in their right mind would expect. and this is not what Java does. No octal floating point number and hexadecimal floating point number, they are there, but they are written using a different notation. When you want to write, for example, A dot B, this is like an hexadecimal floating point number. I chose A dot B, but I could have kept 123.222, okay? Any hexadecimal number that I want to write. If I want to write it using the hexadecimal notation, I prefix it with 0x. So far so good, that still makes sense. And then at the end, I need to have a lowercase p. I'm not sure if lowercase and uppercase are allowed. I don't remember. But you have to have a p followed by a number. And that is the floating point, literal, hexadecimal notation written in scientific notation. Remember the scientific notation for floating point? You use the E letter, E minus 10. That means times 10 to the power minus 10, right? Well, this is the same thing here. But it's not E, it's P. Why not E? I can answer that because E is an hexadecimal digit. So if I write 1.BE2, I don't know if you meant A.BE2 or if you meant A.B exponent 2, right? So I cannot use the letter E. Now, why would I use the letter P instead? I don't know, but that's the syntax, okay? All right, enough exception right now. You're like sick and tired of numbers. Yeah.
What about binary?
That's right. I didn't try binary. Okay. I checked the documentation, the specification of the Java language to double check that slide. I didn't see a binary notation. So I would be inclined to say there's no binary notation either. But that's a little weird. So I'm going to double check on that and I'll follow up next time, okay? I'm kind of like 80% sure of myself on that one, but not 100%. So good question. All right. So let's run this code. Display A. Okay, that one is okay. Display B, the 0 at the beginning doesn't mean octal. So yeah, we have 123.222. Display C. So C and D are not going to be accepted. Okay. Sorry, C is not going to be accepted. D will be accepted. This is a correct version of writing actually an hexadecimal literal. So just a few things to watch out for. Okay, a few things that are, again, if we use common sense, those things would make sense, should make sense, etc. That's the thing about common sense. You can use common sense about how to open a door. If you use common sense in quantum mechanics, you're going to be in some sort of trouble. So common sense is the sense, the logic that is common, and it applies to common things. One of the mistakes that we all do at some point is we think that our common sense is a substitute for being actually well educated in a field. If I don't know actually what Java is doing, I'm just extrapolating out of common sense. I may be right, I may be wrong. In that case, I'm wrong. Same thing for quantum physics too. All right, how to convert from base to base. So the first thing we are going to do is we're going to learn to convert from whatever base notation to back to decimal, back to home, back to the one that we learned since we were like little kid, right? So the rule is we're going to do a conversion here that's going to go from 423 written in decimal to 423 written in decimal. This is going to be spectacular. How do we do that? We take each digit, we've done it already. We take each digit, we multiply by the base x power, the position of the digit in the number. So this is position 0, we start to the right, position 1, position 2. So this is going to be 10 to 0, 10 to 1, 10 to 2, and then multiply by 4, 2, and 3, you get the result. So we know already how to convert from decimal to decimal. Achievement unlocked. So the utility of that is kind of, you can criticize, you're free to criticize. But we can apply the same method, that's where it gets useful. We can apply exactly the same method to convert from, let's say, binary back to decimal. So here's a binary number, 1, 0. So I'm going to look at it in the polynomial form. I'm going to say this is 0, I'm starting right to left, 0 times the base, binary 2, power 0. And then this is 1 times the base power 1, that gives me a 2. You give me a larger number, no problem. I still break it down the same way. This is 0 times 2 power 0 plus 0 times 2 power 1 plus 0 times 2 power 2 plus 2 power 3. That's 8, and so on and so forth. So it gets more or less complicated, okay? You definitely want to reach for that calculator at some point, but if I ask you for a quiz to do it by hand, you can break it down, no problem, all right? So if I gave you, for example, this one here in a quiz or something like that, you can do it like that. If that helps, you can try to make it as a sort of table. I don't know. Maybe some of you are going to be more comfortable using that kind of notation. Go with whatever works for you. What I did here, I did exactly the same thing. Okay, I didn't change the method. But what I said is I have my little table of conversion here to remind me that the powers of 2 are 1, 2, 4, 8, 16. So that I don't have to constantly remember them if this is a problem for me. I write down my binary number, and then I just go column by column, the binary number times the base to the power whatever, and I get my result. And then I add together 16, 8, and 2, and I get 26. Okay? So this notation is okay for you, go for it. You prefer that table, it makes more sense? Sure, why not? Whatever works, but you can do it by hand. You just have to follow that recipe. What about hexadecimal to decimal? So we are going to only talk about decimal, binary, and hexadecimal. Okay? Octal, no, I leave that for somebody else to tell you about it. It's not used nearly as much. That's why. So here's an hexadecimal number, 7F. How do I convert it? We go back to the question from sooner again. 16 power 0 times F. Oh, wait, there's a trick here. What is F? F is a digit in hexadecimal. It has a value 15. Yeah. So 15 times 16 to the power 0, right? That's just for F. Then 7, that one is easy to remember. 7 is a hexadecimal number, digit, sorry, that corresponds to the value 7. So that one is okay. 7 times 16 to the power 1. Sum it up, 127. Yeah. I'm sorry, what? Okay, F is 15 because we start counting. It's a very common question. It's a source of problem at the beginning, right? You start counting by 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Everybody at some point, we all think F is the last one, it's 16. But when you have a base 16, which is hexadecimal, that means you go from 0 to 15. When you have base 10, you don't go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You go 0 up to 9. Okay? Make sense? Right. That's yeah. You start with 8, 10. You remember that one, you'll be okay. All right. So good question. This is actually one of the few things that tricks everyone at least one time. Okay. So I'm glad somebody thought to bring it up. All right. So how do we convert an hexadecimal? I did the little one. Is this one more difficult? No, it's longer, but it's not more difficult. Okay. F is 15. 15 times 16, 0. 15 times 16 to the power 1. 15 times 16 to the power 2. 15 times 16 to the power 3. Add them up together, you get 65,535. That, if you didn't tell me it was an hexadecimal number, I could not guess. But if somebody tells me, hey, here's an integer literal, 431, written using the hexadecimal notation, what's the value of that thing in decimal? Again, I take the 1, I take the 3, I take the 4, that's it. So the one thing that you need to remember, and that's where that misconception comes from. It's not really a misconception, but it's that the digits in hexadecimal, there are more digits than in decimal. So at some point we need new notation, and you need to know that the A corresponds to the value 10, B 11, C 12, etc. Once you do it a few times, like 2 or 3 times, it's going to come naturally. Okay, but the first few times, yeah, it's one of the questions that comes up. So again, quiz question, what is AB93F? Well, it's an integer literal written in hexadecimal form. Good start. What is the value of that thing? Again, break it down. So you write, and now this is more useful, right? The powers of 2, generally we all kind of figure them out, right? And we mess that up like once in a while. The powers of 16, I know that one. Sometimes I remember that one. Yeah. Okay, so after you see them a few times, that's going to become common, okay? So don't worry about that. But you know what? This is why we have open book in the quiz. You have your appendix, okay? So you can have stuff like that kind of pre-memorized there. I write down my hexadecimal number, AB93F, like this, and I go column by column. F is 15, so there is one extra step, sorry. One extra step is if I have letters, I transform them into their decimal value first, and then I do 15 times 1, and then 3 times 16, and then 9 times 256, and so on, so forth, and I add this up together. That gives me 702,783. So that's going from anything back to decimal. Now, the last thing we need to learn is how do we go from decimal to hexadecimal or from decimal to binary? So from decimal to anything else. So it starts here. I know because there's a thing here that reminds me. So this is the number I want to convert. Literal, integer literal 123, okay, expressed in decimal form. And somebody asked me, what is it in binary? So thank you for asking me that question, right? How do I figure this out? I'm going to take 123, divide by 2. That gives me 61. So integer division, right? I don't care about decimal. What is the remainder? 1. That's my first binary digit to the right. So that remainder and integer division, well, at least we have one application of that stuff, okay? If anything else is going to be used here for converting. Then I take that result, 61 divided by 2 is 30. Remainder 1, that's my second binary digit. So I know my binary digit ends with 1 and 1 at the end. And then again, take 30 divided by 2, 15, remainder 0. 15 divided by 2, 7, remainder 1. So I keep dividing by 2, and I look at the remainder, and that gives me the digit. And I can keep the result of the integer division, and that's going to be the next thing that I divide by 2 in the chain. So I go right to left, and I get my answer. Again, another way to look at this, you take 456, sorry, I cannot speak anymore, divide by 2, divide by 2, divide by 2, divide by 2, divide by 2. So you fill that column, that row, sorry, by dividing by 2. You stop when you reach 0. Okay, you don't care about the 0. And then you look at the remainder, and 0, 0. Or you can ask yourself, is this actually an even number? If it's an even number, I put a 0. If it's an odd number, I put a 1. So whichever way works for you, but the recipe to follow, it's pretty mechanical, okay? As a matter of fact, we could write a program that does this kind of stuff. From decimal to hexadecimal, same thing, but you divide by 16. So 123 divided by 16, that gives you 7, integer division again, and a remainder of 11. But there's another trick here. What is 11 in hexadecimal? It's a digit B. So you have to write a B. And that's pretty much all there is to it. If I use the same example, 456, there we go. It's going to give me 1C8. That's the hexadecimal representation. Last one, binary to hexadecimal. Super easy. Here's an hexadecimal number, 7B. To translate in binary, you take each hexadecimal digit, like B, and you refer to that table. What is the value of the hexadecimal digit B in binary? 1011. That's it. So each hexadecimal digit corresponds to 4 binary digits. That's why we still learn hexadecimal. Because when you have to look at a memory dump, or you have to look at a network packet dump, and there's some binary data, it's much easier to look at this binary data in chunks of 4 bits and write them as hexadecimal than to look at the whole binary thing. That's pretty much the number one, the primary reason for which people use hexadecimal. If you have a binary number, you want to translate it into hexadecimal, take a packet of 4 at the end. Look up the table, that's B. Take the next packet of 4 bits, that's 7. Take the next packet of 4 bits, and that's it. Quick practice exercise about those translation. What about we do that with a program? So try to write a little piece of code that's going to actually allow you to display the conversion of a decimal number into both binary and hexadecimal. It's a good way to make sure you know how to do the conversion by hand, and it's also a good way to practice your programming skills. If you have a problem with that, you can work together on it first. It's not graded, post on Piazza, you can come to office hours. Okay? All right. Thank you so much. So make sure to send me a small Canvas message so that I remember to give you the bounty, because technically you are the first one